A very good evening to all my dear audience. I wish you a very happy Eid or Eid Mubarak to all of you attending us from all over the world. It's an amazing participation, and I can see people from South Korea, Philippines, Mexico, US, obviously, UK, UAE, Canada, Morocco, Brazil, Germany, etc. You just name it, we have people. I hope you are healthy and safe wherever you are. And I am thanking you from all my heart for such overwhelming response, despite it's a holiday, but you guys still have joined us. It's amazing. I know in India, it's, like way beyond the work hours, and it might be holidays for a few guys too here. So, you might be a little lazy at the moment or feeling a little bit tired. So what I'll do is start off with a kickstart brain, tweaking session. What I want you to do is hear me out carefully, and I promise it's going to be fun. So this is something that we're going to do for a while now, because we're still waiting for some of the participants to join in us. So while we wait for them, we can play this game. So I'm sure everybody in front of me is, attending this webinar via a laptop or has access to cell phones. So what I want you to do is, hold on, I'll show you my screen, and you can see my screen over here. Now you can go to this mentimeter.com, where you type in menti.com here, and you'll see a screen page like this. Whenever you're done with that, it'll take you to a screen such as this. So alternatively, what you can do is press this QR code, like you can also use the Paytm platform if you're using that to scan this, if your phone does not have a facility to have a QR code over here. And now I will be telling you what the situation is. So here is an example of what we're going to do. What we're going to do is that imagine yourself that you are, in a very hot climate. Say it's in Delhi at the moment, and it's a very hot sunny day, and you're in a school bus. Okay, and you're in a school bus and with 29 other children, and there is a bus driver and you. So you are the only adult who can take a very, very important decision. So you are, in the middle of a charging station, and your co-passengers tell you that, hey, there's a fire in your bus. So what is it that you would be doing, in order to put the situation under control? So let's play this game. So you can put 3 entries per person. It could be a noun or a verb. So while we wait for this, wait for a few more participants to join us, why don't you do this? And we can see the word cloud over here while you type in this. So go to mentimeter.com, use this code 767262, and I can see the participation over here. And just type in 3 words. It could be a noun or a verb that you would do to control the situation. Mind you, there's a lot of pressure in you to save those 29 children in a hot summer day. Hurry up, guys, type in. Woo, escape, emergency, exit. Brilliant. There's only one person who has participated out of so many. Come on. Brilliant. Mm-hmm. Okay. We'll be waiting 5 more minutes. So you have all the time over here. Now you can just, type in whatever you feel like. Great. So we can still continue this, and I will start giving my introduction for the EMF platform. Most of you are really, like regulars in the list. However, I see a lot of new faces, a lot of new people joining in. So welcome once again. So those of you who don't really know what this webinar series is all about, I will give you a brief introduction about what is it. So EMF, which stands for Electric Mobility Forum, is a project which was funded by Shakti last year, and it was inaugurated by the Vice President of India. The three important things that we did in order to accelerate electric mobility in respective Indian states and cities was number one, we do specific convenings and roundtables focused around electric mobility topics. Then number two is scaling, which again, EMF is, the electric mobility webinars are part of it. And we also have a monthly newsletter called EV Connect. So if you haven't checked it out already, please go to check it out. It's quite interesting. The third one that we do is we do mentoring, which means that we do hand-holding with a lot of state governments who are keen and excited about implementing electric mobility in their states and cities. Now, like why these webinars are quite a hit is because as we see that most of the successful countries where there are a lot of EVs are in the colder climates. But, like specifying something or like copying or replicating directly from them could not be a wise idea for us, is because India is a vast country with its own challenges and experiences. So something like custom made and homemade solution would be really amazing. So these webinar topics are really India specific at the moment. Now, out of our experience, as you know that we have been doing this every month since last year, one key change that I would want to, put it out in front of you is that last year we were discussing a lot of things in a very utopian scenario. Okay, if EVs would come, then how are things going to be? Something like that. But now, since this year, the topics are quite real life, like on ground problem based. So, for example, today's topic itself, I know a lot of you have already, registered for the topic, and I don't have to mention it again and again, but it talks about, battery safeties and different kinds of hazardous things that could happen while you're choosing your batteries. And some key topics that you have already registered are hazards with lithium-ion batteries for EVs, challenges with lithium-ion batteries and designs, its mitigation and charging infrastructure challenges. Some of the key takeaways here, which our speaker would be speaking about, is about factors to consider in choosing a battery, types of cell construction, batteries configuration, etc. You would also know about pouch cells, batteries, external short circuit hazards, etc., and many, many more. Mind you, it can get a little bit complicated. However, I promise, and I can vouch for it, it's going to be like a new topic for you, and you will go home with a really, mindful of new information. So, bringing to that, talking about that, we are so fortunate to get hold of a very busy person who is a subject expert in this, and it's not a surprise that you have already seen who is the speaker for today is, but I would be giving a brief introduction about her just now, but I would also request the speaker to give a brief introduction about herself and her organization before we start off with this topic, because I know I wouldn't do such a justice to her wonderful career. So starting, Dr. Judy Devarajan is, research director at UL. You all know what UL is just now, and you will be surprised to know that she has worked in the areas of batteries for more than 21 years with a primary focus of lithium-ion chemistry. Now, what is quite exciting is that before joining UL, she also worked for NASA Johnson Space Center in Houston for 12 years. And she was also a group leader for, battery safety and advanced technology at NASA JSG. She also has an MS in chemistry from the University of Notre Dame and graduated with a PhD in chemistry, specifically electrochemistry, with the University of Alabama. Now she is currently working in UL. So a few logistical things that I would like to mention before we start off the session is, I know, is the most boring part. However, I will tell you again. So, you know, this is a 1 hour session with the presentation with question and answers. I thank you all for doing an amazing job with, you know, like giving in so many questions and comments. They are really exciting. However, I apologize firsthand that I won't be able to take all of your questions. However, I promise to give it to the speaker and publish it on the same link as public query within a week or so. Just give us some time. I will take as many questions possible during the span of this webinar. Second thing is that I am sure you'll be coming up with a lot of new questions in the journey of the webinar. So I would like to mention that please type in your questions in the questions box and not in the chat box. So now the last question that I would like, thing that I would like to do is that you know, I do it and I would like you guys to not do it, is that whenever there is a problem in your internet or you're freaking out that I have missed out on any of the information, then what you would do is that, you know, just don't worry about it, because we'll be having the presentation and the video recording of the same in the same link that you have registered for within a week or two. You'll be getting the notification for the same in your mails that you have registered for. So without taking much time, I start off with today's topic, and I would transfer my controls to Dr. Judy just now. And I hope you guys have a great time learning this. Here you go. Over to you, Dr. Judy.
Thank you. Do I have control over the presentation?
Yes, you do.
Can you see my presentation already? Okay, I can see the control now.
Yeah.
Can you see my screen?
Yes, ma'am, I can see your screen.
Okay, thank you. Good evening to those in Asia. Good morning to those from North America, and good afternoon to those attending from Europe. I'm thankful that you're all able to attend this webinar, and I'm really grateful to WRI and specifically to our moderator, Shravani, for arranging this webinar. My topic today, and before I forget, I would like to wish all those celebrating Eid, Eid Mubarak, and also for all the people who are in the US, happy Memorial Day. Today is a holiday for both, I think, in the US as well as in India, and it's great that we have so many people attending in spite of it being a holiday. Today, under the Electric Mobility Forum, I would like to talk about lithium-ion battery hazards and design challenges for the electric vehicle sector. I'm trying to reduce. Okay. Unable to advance the screen. Okay, there we go. So just a little about UL. UL is a 125-year-old company. It's all over the world, and our mission is to work for a safer world. And as a part of the electrochemical safety group, we are actually also part of the nonprofit side of UL. We do this, or we carry out this mission by doing 3 different things. The first is research, where we conduct research and share the scientific-driven, data-driven knowledge in conferences, and also by presenting in public forums, and also publishing in journal articles and newsletters. We do outreach by conducting battery safety summits and also battery safety council forums. The India Energy Storage Summit that was held last year is an example of the battery safety summits that we've been holding around the world. We also take part in awareness building and education by participating in trainings and webinars, and also sharing our research findings in different platforms like learning modules, which we collaborate with our education team for students of different age groups. So this is an outline of my talk. I'll give a little background, and then I'll talk about the lithium-ion cell chemistry, the hazard causes and the challenges, the charging infrastructure challenges, which is more relevant to the Indian environment, other challenges that you would face when building large batteries, and of course a summary with some recommendations. So as you all know, lithium-ion battery chemistry was first commercialized in the early 1990s. And this chemistry has the highest energy density of all rechargeable battery chemistries. It has no memory effect. It has a long cycle life as well as a long calendar life. And it has very good rate capability. Today, it is used in a myriad of applications, from consumer electronics to electric vehicles and stationary grid energy storage. And you can see it used quite a bit in sea and space applications too. Associated with this high energy density is also the propensity for them to experience fire and thermal runaway if the batteries are not designed or used correctly. And as you will observe, the chemistry of this battery is still being optimized, and there's plenty of opportunity to make material improvements to get better performance. In addition to improvements for performance, we also see that a lot of work is being done on different component areas of lithium-ion cells and batteries to improve their safety. This is a simple schematic of the charge and discharge process for a lithium-ion cell. In general, the cathode of a lithium-ion cell is a metal oxide cathode. It has lithium with a metal oxide. And the anode is usually some form of carbon. It could be natural carbon or synthetic graphite, or synthetic or natural graphite. And the way the lithium-ion cell works is that lithium ions go from the cathode during the charging process and sit in between the layers of the graphite in the anode. And they are held there by what is called van der Waals attraction. There is really no chemical change that is happening. And during the discharge process, the lithium ion goes back to the parent cathode. And the only thing that we see in this particular chemistry is that lithium ions go between the cathode and the anode during the charge and discharge process. And it's sometimes also called the rocking chair battery because of this nature. Some of the factors one needs to consider in choosing a battery is, first of all, the performance. What is the capacity and the voltage that you need for your application? Are there any unique requirements like pulse requirements? And then you also need to look at, what volume you have available or what weight can you manage. So for this, you need to know the volumetric and gravimetric energy density of the system that you're going to be using, the battery system that you're going to be using. Safety is of paramount importance, as we all know, because these are used in a human-rated environment. We use it in everyday applications. The toxicity obviously is very important. Sometimes toxic gases can be emitted from these batteries, and so one needs to be aware of what types of toxic gases come out of them. The thermal capability is extremely important, especially in environment like the Indian subcontinent, where you can have extreme hot and cold temperatures. So one needs to understand, what needs to be done in order to keep it safe and also for it to perform well in those extreme environments. The cycle of service life is obviously very important. You want it to meet the cycle life, the number of cycles that you want it to work for. And calendar life actually is determined by all the components that go into making a cell or a battery. And typically, this is given by the manufacturer because the manufacturer knows how long a particular component will last in that particular cell or battery model. Lastly, I've got the cost because typically we don't like to have the cost affect any of the other things, but cost is an important factor because all these other factors that you consider go into determining the cost of the battery also. This chart provides the components of a cell. The main components in a cell are the cathode, which is the positive electrode of the cell, the anode, which is the negative electrode of the cell, the electrolyte, which is the medium that provides the ionic transport between the positive and the negative electrodes, and the physical separation between the two electrodes, which is provided by the separator, which is usually a microporous material. There are many types of cell constructions. The three main ones are what I've shown here. The one that was first used extensively was a cylindrical cell design, and or later the prismatic metal can cell design came, and then after that the prismatic pouch format cell design came. So the internal construction can be spiral bound or it can be stacked type electrodes, especially for the prismatic cell designs. Or they can be what is called a Z-folded with electrodes folded or stacked, as we see with prismatic metal can or pouch cell designs. The model designation for lithium-ion cells is quite different from what we are used to in a traditional manner. What we had before was calling cell sizes as A or double A's or triple A's, C sizes and B sizes. But lithium ions have a very unique way of designation. So the IEC 61960 standard identifies it as in the following manner. The battery identification includes 3 letters and 5 numbers for cylindrical battery, or 6 numbers for a flat battery, which is a prismatic cell, which can be either a pouch format or a metal can format. And I'll just give one quick example. An ICR 18650 represents a cylindrical lithium-ion cell, which has a cobalt cathode. The C in the 3 letters symbolizes the cobalt cathode, and it has a diameter of 18 millimeters and a height of 65 millimeters. When we look at a lithium-ion cell, a typical nominal voltage for that particular cell is about, it can be about 3.6 or 3.7, even 3.8 volts. But the capacity depends on the volume of material you have inside the cell. And when you look at, but you can actually increase the voltage or the capacity by putting the cells in series or in parallel or a combination of both. In the first picture I have at the top, there are 4 cells that are in series. And when you put cells in a series configuration, they can also call it a string. The voltage is actually additive, but the capacity remains the same. When you have cells in parallel where you're connecting all the positive terminals together and all the negative terminals together, we call it a bank of cells or a parallel configuration. And in this case, the capacity is additive, but the voltage remains the same. So one could use a combination of these to get a higher capacity and a higher voltage. Just have a quick picture in the bottom where it shows a single cell and then 3 cells in a module which are in a bank. And so we call it a 3P configuration. And then the last one, which where you really cannot see the details, is because it's a completed battery pack with the BMS and all the connectors, is where we have the 3-cell bank, where 4 of those 3-cell banks are connected in series to give the 3P4S configuration. As you all know, there are several battery chemistries that are available. Silver zincs are very common. Lead acids are very common too. And the NiCad and metal hydrides were used extensively for power tool applications. Today, lithium ion is more common in most of our applications. So I'm going to spend most of the time talking about this. The trends for cathode materials show that there are many different types of cathode materials that are available today in the market. The first one discovered was obviously the lithium cobalt oxide, but then lithium nickel oxide came into being, and lithium manganese oxide also was used for high rate applications. But today we see several different combinations where mixed metal oxides are also used. Some of the commonly used ones are the lithium nickel cobalt aluminum oxide, which is also called the NCA, and the lithium nickel metal cobalt lithium nickel manganese cobalt oxide, also called the NMC. For high rate applications, a lithium iron phosphate cathode has also been used extensively because even though it gives a lower working voltage range, it actually has very high rate capability, and it is a little safer compared to some of the other oxides, lithium metal oxides. The picture on the top where you see the specific capacity shows that each of these cathodes can give a different working voltage range for the batteries that you're building. The one on the bottom also is a figure that shows the accelerated rate calorimetry self-heating trends for some lithium-ion 18650 type cells that have different cathode chemistries. And what this shows you is that compared to a lithium cobalt oxide, which has a high self-heating rate, the lithium iron phosphate is very benign. It just says that in comparison it's benign, doesn't mean that a lithium iron phosphate is completely benign. In the same manner, anode materials can vary quite a bit too. We have graphite, which was traditionally used, but lithium titanate was also used in some high rate applications. With lithium titanate, you actually lose a lot of the working voltage. The voltage range is very much lower. The nominal voltage is also much lower than if you use graphite. Today, a lot of cells have silicon as the anode. When silicon is used by itself, you obviously get a very high specific capacity, but the issue is that silicon expands significantly and also cracks. And what people have done is they have coated silicon with carbon, so the silicon carbon composite has actually helped to reduce the initial irreversible capacity loss. So people are trending to go towards silicon, towards the use of silicon in the anode. The electrolyte is, as I mentioned, is a medium which helps with the transport of ions between the electrodes, and usually it's a combination of solvents with an electrolyte salt. And the typical electrolyte salt that is used in lithium-ion cells is the lithium hexafluorophosphate. People have tried other salts but have always come back to the hexafluorophosphate. You might see small quantities of additives that are used depending on the need, whether it is a high rate application, long life application, or different temperature or thermal environments that need to be, that the device needs to be used in. And I've just listed a few of the carbonates that are typically used. It could be straight chain carbonates, or they could be branch carbonates, as you see from the picture below. In some cases, other additives are also used, which are other solvents, where you could have esters or other organic solvents. The separator used in lithium-ion cells are also of different types. One could use just a polyethylene separator, or the tri-layer separator, which was very common for many decades. And the tri-layer separator has polyethylene that is sandwiched between two layers of polypropylene. And with this particular design, as you can see from the picture below, it's called the shutdown separator, where on the left side you can see the pores in the unactivated separator. And this picture is a SEM picture, scanning electron microscopy picture, that shows the pores in the separator of a fresh separator. And the one on the right is an activated separator, where the polyethylene has actually melted. Polyethylene melts at about 130 degrees C. And when it melts, it shuts down the pores in the separator. And so the ions are not allowed to move between the two electrodes, thus making the cell safer. More recently, we've seen that the polyethylene separators are coated with an alumina coating. This seems to strengthen the separator. And in some cases, we see that both sides of the separator are coated with alumina, and in some cases, we see that only one side of the separator is coated with alumina. And I have some SEM pictures on the bottom to show that, where you can see the weave of the polymer separator in the one that has no coating, and you don't see the weave with the one that has the alumina coating. Lithium-ion cell construction, as I said, is of three main types, the cylindrical, prismatic, metal can, and the prismatic pouch formats. With the metal can cells, there is an internal protective device, which is called the current interrupt device, that actually helps under over voltage or overcharge conditions. And the way the device works is that when the voltage of the cell increases, there is an additive lithium carbonate that had been added to the lithium ion cells. And so it above a certain voltage, this produces excess carbon dioxide, and the pressure inside the cell increases, thus moving the two discs of the CID apart. And at this point, it's an irreversible action where the mechanical touching of the two discs is disrupted. And when this happens, you have a dead cell and you can no longer charge or discharge the cell, but we call it a fail-safe mode because the cell has failed in a safe manner. The same type of device is also found in a prismatic metal can cell. When we look at a prismatic pouch format cell, that type of device is not placed in the cell. The other safety device that is placed inside the header of cells, especially the cylindrical cells, is a PTC device. This is actually a polymeric material that is sandwiched between two stainless steel plates that looks like a washer. And when you have a high current or high temperature that goes inside the cell, that the cell experiences, then the polymer expands and increases the resistance of the cell, thus limiting the current going in or out of the cell. And this is a resettable device. Once the fault is removed, the PTC actually goes back to its original size, but we never get back 100% of the PTC resistance that it was before that activation happened. And there are limitations with this, which I'll also talk about. With the prismatic pouch cell, it is protected mostly against a hard external shot, which is a low impedance shot. By the way this is done is one of the tabs, the one which has a lower melting point, actually burns off when you have a hard shot on the cell. Other than that, it does, and again at this point, the cell is in a fail-safe mode, but because you cannot charge or discharge it since the tab has burned off. I have seen in very rare cases where there is a circuit board that is actually attached between the tabs of the pouch format cell and its application, and this particular circuit board can be placed physically on the cell itself, and in those cases it actually provides protection against overvoltage and undervoltage as well as overcurrent. But in the picture that I show here, that is not actually available. So lithium ion hazard causes can fall into three main categories. One is the thermal hazard cause, the other is mechanical hazard cause, and the last one is electrical hazard cause. I'll talk a lot about the electrical hazard causes, and I'll touch on the thermal hazard causes also, but not much on the mechanical. As we all know, lithium-ion batteries were first used for consumer electronic devices like cameras, camcorders, laptops, and so on. But today, we use them in high voltage and high capacity applications, as with electric vehicles and in stationary grid energy storage applications. An interesting part about this is that in many of these high voltage, high capacity applications, we are still using cells that were designed for consumer electronic applications. So, some of the things that I will cover today are how that can affect the safety of the battery. I have some pictures of lithium-ion fires on the right, and you can see that even with a single cell, as with that found in an electronic cigarette, there can be extensive damage to both the person as well as to surrounding. Like if there's a fire with a single cell, you can have the carpet and the couch and the drapes burning. And we've seen lithium-ion fires with other portable applications like hoverboards. We've seen them burn down shops. We've seen lithium-ion fire incidents in cell manufacturing facilities as well as in battery recycling facilities. So this picture shows, this chart shows the general charge and discharge characteristics of a lithium-ion cell. Typically, a lithium-ion cell is charged using a constant current and constant voltage protocol. And at the end of the charge process, when you look at an anode, you'll see that it has a gold color. This shows that lithium ions have actually intercalated into the carbon matrix, and that provides a gold color. When the discharge happens, when all the lithium ions go back to the parent cathode, then you'll see that the anode is now, has no lithium ions, and so has a grayish black color. And again, I wanted to emphasize that depending on the rate of discharge, and again, this depends on any pulses that you might have, the discharge curve can actually shift quite a bit. And this is something you need to take into account when you are designing your battery pack and how you want it to be used. There are many challenges for lithium-ion batteries. First of all, the cell and battery components, which are the active as well as inactive components that go into the manufacturing of a cell or a battery, can vary quite a bit. And as we all know, there are various cell sizes and formats that are available. And also battery sizes and configurations are found in plenty. And to make all of these, we need tens of thousands to sometimes billions of cells and thousands of batteries that need to be manufactured. And this is sometimes done within a month or sometimes within a few days too. And the biggest challenge is to screen and match every cell that goes into building a battery, and also testing all the cells and batteries that are manufactured before they leave the manufacturing facility. And lastly, testing in the relevant configuration and environment is very critical, and it's a big challenge because it is not always possible. But from our extensive safety and performance testing in the past more than 2 decades, we found that the cell level controls do not translate to module or battery level controls. And we also learned that all the safety controls need to be verified by testing at the appropriate level or the configuration and in the relevant environment. What we have found is that hazards such as overcharge and external short have opposite outcomes in pressurized versus non-pressurized environments due to the difference in the heat dissipation. So quickly going through the electrical hazards, the first one I'll just mention is the overcharge. This is when you have a high voltage or over voltage or a high rate charge. You can have electrolyte decomposition, cathode destabilization, lithium dendrite formation, which then leads to high temperatures, venting, fire, and thermal runaway. When you have an over discharge, there are 2 things that can happen. Dissolution of copper from the current collector, copper current collector happens. And if you do an extreme over discharge and it goes into negative voltages for prolonged periods, you can actually dissolve copper and deposit it on the cathode, anode, and separator. And it can, the electrochemical system now becomes an electrical wire, and you have a short inside the cell, but it's a benign internal short. And the cell dies, you cannot charge the cell anymore. But in some cases, you have subtle over discharges where you're just going slightly below the manufacturer's specification through your cycling process. And at this point, when lithium ion tries to intercalate into the anode, it might not be able to do it because copper has spread on the anode surface. And so it deposits as lithium metal. And in those cases, depending on the extent of the over discharge and the cycling, and of course the temperatures too, one can have a sudden thermal runaway that results, and people will not understand why it happened unless they have the right data collecting capability, which they can analyze later. The external short hazard can be of the high or low impedance type, and I'll talk a little bit about it a little later. The internal short is something that is very elusive. It's not easy to always detect, and it's not actually easy to protect from also. There are 2 main ways you can have internal shorts created. One is due to manufacturing defects, especially those that were not caught during the testing of the cells and batteries in the manufacturing facility, especially the cells. Sometimes subtle defects cannot be detected, and then they can manifest themselves in the field. They can become nucleation sites for internal short creations. Another way that feed failures can also happen is if you use cells beyond the manufacturer specification, or if they're not designed and used in a correct manner. I've shown some pictures here of defects that are found and that we have found in lithium-ion cells. We've seen iron particles that were not supposed to be there. We've seen tears in the separator, salt deposits. We've seen aluminum left over from tooling, aluminum specks. And then we've also seen some damage to the anode current collector with a hole in it. So I wanted to talk a little bit about the overcharge hazard and how the internal protective devices do not always protect. As I mentioned before, in a single cell, the current interrupt device activates 100% of the time when you have an overcharge condition. But what we found is that when we put cells in series or in parallel connections, then it no longer works as expected. In this particular case, we have 14 cells in series, and we found that the cells went into thermal runaway, catastrophic thermal runaway, with temperatures above 500 degrees C. And when we did the same test under a vacuum condition, we found that there is benign CID activation of every single cell. So the heat dissipation that occurs in an ambient condition versus a vacuum condition really changes how that CID, whether that CID actually is a catastrophic, results in a catastrophic failure or not. Also wanted to show that what happens in a single cell does not always have to translate to a module or a battery level. In this particular study, we studied a pouch cell and overcharged it with a 1C equivalent current and then a half C equivalent current. And under both conditions, it went into a catastrophic thermal runaway with a big fire. But when we overcharged it with a C/3 rate current, which was 0.9 amps, we found that it just the cells just swelled. And so we took that same equivalent current and tested it with a string of 9 cells and a bank of 8 cells. And in both cases, we found that all the cells went into catastrophic thermal runaway with a big fire. And we, as you can see, post-test, there was no cell left behind. So I just have a couple of videos that I would like to show. Sometimes people talk about pouch cells being very benign, but as you can see, because of the low pressures that a pouch cell has for bursting, it can give out liquid electrolyte or vapors that fall on the surface of a hot pouch and combust very quickly. So you can have a big fire where it burns till all the electrolyte is burned. This one is also showing you just 4 cells in parallel that have been tested under an overcharge condition. And as you can see, with even just 4 cells, you can have a catastrophic thermal runaway. So the takeaway here is that battery designs should be to fault tolerant to over voltage and over hazard, and the cell level controls do not translate to module or battery level. You have to test in the relevant battery configuration and environment. Cell level monitoring and control should be incorporated into the battery management system. Also, the cell internal protective devices have limitations which you need to understand, and they should not be relied upon unless it has been tested at the right level. Just quickly going into the over discharge, I talked about subtle over discharge and significant extreme over discharge. As you can see from some of our pictures here, there can be decomposition of electrolyte at lower voltages, and in the case of pouch cells, it's very visible with pouch cell swelling. We've seen, with continuous over discharge and recharge, we have also seen a lot of damage, heat damage in the separator as well as in the cathode and the anode, as you see from the pictures here. So the takeaway from this is that over discharge or under voltage protection is absolutely needed at the cell and battery level for all applications. And if you do stringent cell screening and matching, then you can avoid the deviations in voltage between the cells, and thus prevent any one cell from going into lower voltage than the other cells or going into an overdischarge condition. And cell balancing also helps with this to keep the cells balanced within a small delta voltage value. The external short, I mentioned, it's like an electrical shock to the cell or a battery, and it can be either a low impedance or a hard short, where the internal resistance is equal to or less than the battery, or it can be a soft short, where it's a high impedance and the load is higher than what is specified by the manufacturer, but it's not lower than the internal resistance of the cell or the battery. And both of these can lead to high temperatures, venting, and fire. And what we found is that the internal protective device in an 18650 cell, which is a PTC, has a voltage limitation. At a single cell level, it works 100% of the time, and it's resettable. But when we put cells in series or in parallel connections, we found that the PTC ignites. And this is because it has a threshold voltage limit. When a PTC activates in a high voltage environment, it actually ignites. And when you have a hard short which is creating heat and the PTC is igniting, you can have a catastrophic thermal runaway. So again, we need to understand the limitations of the protective devices, test in the relevant configuration and environment, and make sure that the protective devices are working. Heat dissipation between the cells is quite important. We have seen that in this particular case that I showed, we saw a lot of charring and electrolyte leakage, but we didn't see a big fire. But when we tested the same string in a vacuum environment, we found that the cells go into catastrophic thermal runaway with a big fire. And so you just need to test it in the right environment. And coming to the high impedance short circuits, one cannot put too many fuses. So it would be nice to have what we call a design for minimum risk, where you take care of all the different factors that can go into mitigating the risk of short circuits. You do the anodization, you size the wires, cables, and connectors appropriately. Make sure there are no sharp corners in your battery design, so there is no shaping of wires or cables. In that way, you can actually save or reduce the risk exposed that are imposed by short circuits. For the internal short circuits, I already talked about the manufacturing defects and the field failures. So the cell screening methods and criteria in cell manufacturing and battery manufacturing facilities should be extremely stringent, and they should be screened. Cells should be screened before they're put into batteries. And also, if the cells and batteries are used conservatively within their specifications, that will help a lot with preventing internal shorts from developing. The high and low temperature hazards, we have high temperature hazards, which can, the high temperatures can cause electrolyte decomposition and gas production in the cell. It can also cause cathode and anode destabilization, which can then lead to venting and fire. When we look at low temperatures, again, this depends on what the manufacturer specifies as low temperature that they can work with or the cell can work at. If you go below that, the electrolyte viscosity usually increases, and this increases the resistance for the flow of ions that can then result in lithium dendrite, metal dendrite formation, because the lithium ions have had a difficulty in intercalating within the anode electrode. And so the best thing is to characterize them at the manufacturer's specified extreme temperatures and confirm that they work in the environment that you want it to work. And carry out some destructive testing to see if any severe degradation has taken place. And if there is, then you can make changes to the thermal conditioning that is happening to the cells and the battery, so you can improve the design. Thermal modeling also helps quite a bit with understanding, where you need to put your thermal sensors and what the heat dissipation paths of your battery are. I would usually recommend a really small thermal gradient within the entire battery. I recommend 5 degrees F, which is really difficult to get, but that has been something that we have imposed on some of our applications in my previous career. Some of the other challenges, again, with temperatures is that when we have cells like in the Boeing 787, where we had rivets that the terminals were attached to, we noticed that depending on the temperatures, different cells, the rivets on different cells had a strain. And we also noticed that when you have high currents going in or out of the cell, the electrodes that are attached to the terminals can get pretty hot inside the cell. And the current collector getting hot can also melt the separator in certain portions of the cell. So challenges with the charging infrastructure and process is what I'm going to talk very briefly about. There are three main aspects to this. One is the business aspect, and then we have the technical aspects, and then we have the regulations and standards. When we look at the business aspects from an Indian environment, we see that there can be private ownership with private or public charging stations. And also battery swapping has been significant item that has been talked about in the Indian environment. And then there are other technical issues like recognition of the right charge protocol, the state of health of the battery, and the age of the battery. And of course, the big challenge of regulations and standards. And the reason I was talking about the charge protocol is because, as I mentioned earlier, depending on the cathode chemistry, and here I've only showed the cathode chemistry, this can change with anode chemistry too. You can see that a cell can be charged to 4.2 volts if it's a lithium cobalt oxide, or 4.35 volts if it's a lithium NMC cathode, or to 3.6 volts if it's an iron phosphate cathode. So one should be able, the charger should be able to recognize the charge chemistry. Here I want to show that the voltage curve actually changes when the cell ages. And as you can see with age, the same voltage is reached, the end of charge voltage is reached faster during the charge step. And of course, discharge time is also reduced. Another thing that I wanted to point out that is significant is using it in a voltage range that is shorter than what the manufacturer specifies. When we reduced our voltage range of operation between 4 volts and 2.9 volts, what we found is that this is a 200 millivolt reduction on either end. What we found is that we more than double the number of cycles that we get from the battery. So in terms of recommendations for the charger or the charging infrastructure, we recommend that battery should be independently fault tolerant, and the charger should recognize the relevant chemistry of the battery and use the right charge protocols for charge and discharge. And the end of discharge voltage should be prescribed if the charger is doing maintenance cycles like charge and discharge. And then if one of the batteries is over discharged, it should not be automatically recharged unless someone understands what went on with the over discharge battery. And once the charge is complete, the charging the current should be completely cut off. There should be no trickle charging. The health check of the battery should be performed before charging is starting. Age of the battery should be taken into account, and the charger should also have additional protective controls for monitoring cell and battery voltage, current and temperature. Cell balancing is very important for a charger. So you can keep all the cells in sync with each other, and you prevent any overcharge or over discharge of any of the cells. And another important thing is to protect the charger against any current backflow from the battery into the charger. And lastly, I would recommend that a fire extinguishing method should be provided in the locations where this charging infrastructure is assembled or placed. There are some environmental challenges that are, I think, also important in the Indian environment, which is with respect to altitude. This particular example is just what I want to show you. It's only an example. It doesn't pertain to your environment. But what I wanted to show is that when you have a pouch design cell, you have to have restraints on the pouch. And if you look at the example that I've given here at ambient pressures, what we found is that after 500 cycles, we lost on less than 4% of the capacity. But when we test it or cycle it in a vacuum environment, within 30 cycles, we actually lost 8.9% of the capacity in a restrained mode and 29% of the capacity in unrestrained mode. So there is a difference between placing restraints and not placing restraints, but there's also a difference in the altitude or the pressure that the environment is in. And the next page shows a little bit more of a realistic one for your environment, where you are using an electric vehicle in a high altitude setting like a mountain top, or a high or a tall hill or a mountain. And you can see that different manufacturers have different designs, and so the pouch cell can expand to different degrees, and capacity can be lost to different degrees. So restraints on the flat faces of the pouch are absolutely important. And last thing that I wanted to talk about is heating and cooling systems for battery packs. If you have a really large gradient in the thermal environment within the battery pack, which is between the cells, then you can have deviations in voltage, capacity, and internal resistance, and eventually the safety of the battery becomes a question. And I want to show you a quick example where this was a real case. It was a truck battery where they had 6 modules with a BMS, with 3 different BMS monitoring different modules and balancing them, but there was no central BMS that was actually monitoring all 3 of the other 3 slave BMSs. And they had a forced air cooling system that was going in from one end of the battery to the other. And what they found was that modules 1 and 6 were getting very hot, especially in a cold environment when it was snowing outside. And this is big. There are 2 reasons because of, in this case, the forced air cooling was actually not effectively cooling the battery, all the modules of the battery. And the second thing was that the BMS was really not monitoring all 6 cells and balancing them for the variations in temperature or the cell balancing that it needed. So some of the cooling systems that you can see today are of the active type or the passive type. And the active cooling system can actually, can look like this. There are many different designs that one can provide for active cooling systems. But they can be, with air or liquids or some other gases. And then the passive cooling system is something where you can use a phase change type material that can remove heat from your battery pack. And again, depending on the application, one could go with an active cooling system or a passive cooling system. For instance, with 2-wheelers and 3-wheelers, the passive cooling system might be something that will work very well. But for 4-wheelers and larger trucks and so on, the active cooling system might be the way to go. Some of the challenges that are associated with them is that you could have liquid leakage that can then cause a problem in your battery pack and inefficient cooling. And with respect to heating systems, that's another thing that is needed, especially if it is a very cold environment. You need a heating system that can heat your battery up to a certain value before it gets charged, to a certain temperature before it gets charged. And in this case, sometimes the challenge is that if your heating system fails, then your battery can have uncontrollable heat. And so that needs to be taken care of by reducing the wattage of the heater that you have. And then you also have the issue that sometimes your heater is powered by the battery pack, then you're actually draining your battery pack, and that reduces the life of your battery pack. So having a cooling design that provides the smallest possible thermal gradient in your battery should be chosen. Just quickly go through other challenges. You have high voltage safety, you have complexity of the sensing systems that are used in the BMS. The quality and relevancy of the sensors or the electronics and protective devices and the software is also very important. Transportation safety, obviously, when you're transporting batteries that are large, especially for electric vehicles, there are several standards and regulations that need to be followed to make sure you're transporting the batteries in a safe manner. Stranded energy has been a big issue with electric vehicles in other countries, where you have half the battery that has burned, and you don't know how much energy is remaining in your battery and how to dissipate the energy in the battery. Environmental pollution and toxicity, you're familiar with that. Flammability and off-gassing also is something that you're familiar with. It's very more critical for enclosed systems like in stationary grid energy storage applications. Fire extinguishing methods are something that have not been optimized for lithium-ion batteries. Of course, we all know that a lot of this has been done with different fire suppressants. And what we find is that copious amounts of water is the best fire extinguishing medium. But if you look at the Indian environment, I have been asked questions about is salt water okay? And you've got to think about that, because that can also cause a short circuit. And if you are pouring salt water on a high voltage system, you could have arcing and sparking and fire before the water actually dissipates all the heat in the battery and cools it down completely. So those are things that still need to be studied. And so I would say that the future studies should include some of these realistic environment methods of suppressing the fire. So in summary, I would like to say that one needs to design and use the cell or a battery within the manufacturer's specification for voltage, current, and temperature, and also qualify it with ample design compared to what you need for your application, and ample margin. Batteries should be independently fault tolerant unless they are embedded into the hardware, where the device can provide additional levels of control. And then faulty design, use, or misuse need not lead to immediate catastrophic failures. It usually is a cumulative effect, and that can result in a sudden catastrophic event. And what we have seen is that reducing the voltage range compared to what the manufacturer even recommends can actually increase the battery life, health, and safety. And complete characterization of performance and safety of lithium-ion cells and batteries should be carried out by testing, and it should be tested in the appropriate configuration and environment. And one should be vigilant to off-nominal behavior and be able to recognize any off-nominal behavior during the life of a battery. So the defective cells or batteries can be removed from service before it goes into a catastrophic failure mode. And again, emphasizing that it should be used within the manufacturer's specification, and there should be appropriate monitoring and control, as well as balancing. And the thermal design is key to prevent subtle defects from turning into nucleation sites for larger fault conditions. So just emphasizing that you should design conservatively and test stringently. And I would like to thank my team at UL, Saad, Rindu, Tapesh, and Daniel for all their help in putting this presentation together. And thank you for listening. Now I'm open to questions.
Thank you, ma'am. I know this is such a complicated topic, and I really appreciate that you were able to finish it off before time. And also you've covered all the key points that we had mentioned in the registration link with spot on takeaways. So that's really commendable. You've done some kind of a magic. I see that, like we're already running short of time. However, I'll, take the most interesting questions now. So the first one would be somebody from India who is asking, what would be your recommendations for strategic management systems for cooling requirements for different vehicular segments, such as two-wheelers, three-wheelers, four-wheelers, buses, and HGVs?
Sure. I touched briefly upon the cooling systems. What I would recommend is that one has a passive type cooling system for two-wheelers and three-wheelers, where you have the phase change material that can actually absorb any excess heat that is dissipated that is produced in the cells. So you can dissipate the heat outside. And for larger vehicles, I would recommend that active cooling systems be used with maximum area where the coolant can remove the heat from the cells. So one should actually try some thermal modeling to understand how the heat is dissipated from the cells with active cooling system loops that are designed specifically for the cell design. As you saw, with cylindrical cells, the way the cooling system removes heat is different, because the cylindrical cells dissipate heat from in the axial direction, which is the top and the bottom of the cell, whereas a prismatic cell typically can dissipate more heat from the flat faces. And so the cooling system, needs to be studied, and thermal modeling helps a lot with that. So I would say, passive cooling systems for the smaller two-wheelers and three-wheeler batteries, and active cooling systems for the larger vehicles.
Brilliant. Coming to the next question is a question that I have received from many countries with similar climatic conditions, enthusiasm rate, and similar fleet size as ours. So they had asked this question, and I'm putting it in front of you, is that, do we have enough demand assessment and training with the fire safety departments? If yes, if no, and if no, then what would be your recommendations in the planning stage of several guidelines or policies regarding the training and demand assessment of the fire safety departments? Yeah.
So that's a good one. So there aren't any completed documents. Of course, the NFPA 855 talks about what you need to do in the case of a fire. But there aren't optimized fire suppression methods. So I think every country needs to develop its own methods, because the fire service is different. Fire suppressants that are available are different. The environments are different. For instance, on a road in the US or in Europe, it may not be as, the vehicle can be isolated. But then, you can work on a fire suppression method, but in a crowded country like India, where the traffic is heavy, you may not be able to move your vehicle from the center of the road to the side to be able to put it out in an effective manner, and it might be a really catastrophic event. So based on the environment and the country's needs, one should actually work with the fire service to come up with a more effective method of putting out a fire. And also, I had also mentioned stranded energy. One needs to understand how one is going to approach a burning vehicle or a half-burned battery. People need to understand, the health of the battery, which parts of the battery are energized and which ones are not, and see how they can actually de-energize the battery before they move it to a location that is safe. So I would say from, at this time, fire suppression methods for vehicles have not been, as well as for energy storage systems, have not been optimized, but there are good fire suppression methods that are being looked into, like water, as well as some people are also using carbon dioxide, cold carbon dioxide gas and cold nitrogen gas. Again, when you get into those kinds of gases, you've got to worry about toxicity and environmental pollution and so on. So there's a lot of work that needs to be done in that regard. And I would be, it'll be pleasant if, or a nice thing if the government actually funds some of those research efforts, so we can get better methods that the fire service can use and the first responders can use.
Sure. So the next question is, this is more from the perspective of a circular economy, and this is a question from different kinds of, battery manufacturers and aggregators. So the question is, what are the things to keep in mind before disposing these kind of batteries? And even before that question, the question is that whose responsibility is it? Like, once you sell off the battery or the vehicle, and once it reaches its survival rate, what do we do with it? Like, do we have enough markets and other, enough trainings? So what do you think are the things to keep in mind before throwing them off? And are there enough disposal facilities, like in terms of infrastructure, for example, scientific landfills, infrastructure, and enough safety protocols or standards? So over to you.
Sure. So with respect to recycling, I think, or disposal, I think that's a very significant factor, especially today when vehicles have a mixture of lead acid batteries and lithium ion batteries. It's very important to confirm that when people are disposing the batteries, especially for recycling, that they put them in different recycling bins. When you look at how lead acids are recycled, they're actually first crushed before recycling happens. But with lithium ion, if you crush a lithium ion cell, it can go into flames and have a catastrophic thermal runaway and fire. So we have seen several recycling facilities burn down because of this type of mixing of battery chemistries. So having said that, that is very important that people segregate the battery types for recycling. The other thing is, who is responsible? That's a question that has been asked globally. Um, and I'm here just going to give my opinion. What I think is best is if the government provides incentives for the car owners to dispose the batteries in a specific location. Manufacturers are actually today of lead acid batteries are actually given incentives, or there's a regulation that says so much of your battery should be recycled, and they do it. In a similar manner, today people do not want to have responsibility for recycling a lithium-ion battery, and so the question has been asked several times as to, who is responsible for it. But I think if owners of vehicles are given some type of incentive for returning their battery to the manufacturer or to a disposal facility or a recycling facility, I think that will help a lot in keeping the environment greener and also replenishing the materials that one needs in making a lithium-ion cell. So that's just, I know that this is in work and this has been questioned a lot, but I think just like, how we pay people when we take their glass bottles or their metals, it'll be nice to have some type of incentive when people return their batteries.
Great. This comes to the second last question, which is mostly from the automobile sector, the charging sector, charging infrastructure people, and also some of the consumers. They are asking, and these guys are mostly from India, and specifically from the northern part of India, namely Delhi. So they are asking me to imagine, like a North Indian city where we have extreme hot temperatures and extreme cold temperatures, like in terms of harsh winters and summers. So they want to know, how does temperature play a role in battery safety? And I know you have already mentioned this in the webinar throughout your presentation. However, they would like to know what are the tips for battery performance, for better battery performance, long-lasting ones, like some key do's and don'ts. So over to you.
Sure. So keeping the battery at stable temperature closer to ambient, which is about 20 to 25 degrees C, will not only save the battery in terms of its health, but it also gives better performance and longer life. So to do that in extreme environments like very hot or very cold temperatures, you need external features like cooling systems and heating systems to keep your battery under that same conditioned thermal environment. So I would say, for extreme hot weather, one needs to have an active cooling system that will provide cooling continuously to the battery. And in terms of the very cold temperatures, you have to have a heating system. And this is something we actually see, in our environments too, in the US, where we have very cold winters and very hot summers. And in the cold winters, you have to warm up the battery to a certain temperature before you can actually charge or discharge the battery. So that is really important, that you do not try to charge a battery when it's very cold, because as I mentioned before, the internal resistance of the cell increases because the viscosity of the electrolyte increases, unless that electrolyte is actually made to work at really low temperatures, like less than 0 degrees C. So one should provide for both, especially if you have a weather that can go to either extremes. So the heating should be done. So and the charger should look out for the temperature of the cells or the battery pack before it starts charging the battery. And confirm that it is within what the manufacturer would like for the battery or the cells to be at before it starts charging the battery. And the cooling system obviously is very important to keep a cooler temperature environment for the cells. And again, like I said, it helps with lessening the gradient, thermal gradient between the cells, which then if you have a higher thermal gradient, it'll increase the internal resistance of the cells depending on the thermal environment. And so that can cause an imbalance in the cell with respect to voltage, capacity, and so on. And then it can result in a safety hazard. So I would say for extreme and thermal environments, both the heating and the cooling system are very important.
Okay, that brings us to the last question. So before I, put out the last question in front of you, I would request the audience to, follow these instructions. Go to the Mentimeter as I've instructed earlier, and then put on this code. As you can see on my screen, you can put on this code. And now, after learning from this presentation, after Dr. Judy gave such a beautiful insight on the topic, what would you do here? And I would request you guys to kindly maintain the decorum of the event. I know it's quite fun to be mischievous, but please, please, please only type in sensible answers. It could be 3 words, it could be a verb or a noun. So imagine yourself in a hot sunny day in a charging station with 29 children in a school bus, and the bus gets fire. So what would you do? You being the only adult. As the audience types in, ma'am, I would like you to answer this question. This is mostly from the common people, actually. So this is, what are the roles to be followed by common people to ensure safety in home charging and public charging?
The things, that actually, will depend on the government regulations. But I think the important part about maintaining safety in whether it's private or public charging stations is having, all the controls in place, including all the mitigation measures. One of the things that one has to consider is, spacing between different vehicles. One has to consider, where people are standing while the charging is taking place. One has to make sure that there are no power outages that happen during the charging process, and if it does, that the charging should be shut off in a very safe manner. And also the fire mitigation methods or the fire suppression methods should be available in every charging station, whether it is a public or a private location where the charging infrastructure is placed. And again, when you get into battery swapping, that has similar demands with respect to safety. It actually has additional, I would say, additional demands, because now you're looking at the batteries that come in with different age, different health, and exposed to different environments and so on. And so that particular infrastructure has additional requirements to make sure that that it's actually looking at the health of the battery and the age of the battery and so on, and also the chemistry of the battery to make sure that it's using the right protocols to charge and discharge the battery. So I think all those I think can be made more effective, especially in India, where the government sets the rules and the regulations. If these are developed with right input from the right people and imposed on everyone who's using either a public or a private charging infrastructure.
Thank you, ma'am. Before I come to the end of the webinar, would you like to reflect upon, like in 2 minutes or 1 minute, about what the audience has put in after your presentation? Do you think it was useful? What are they saying? Any of the, recommendations from them seem to be quite need of the hour based emergency solutions?
Okay, I will have to look at the chat. Okay.
So a lot of people are saying use 911, evacuate, use fire extinguisher, evacuate all the kids. So what would you think would be the best possible solution, like in 3 words? What would you type in if you had to put in any 3 words naming a verb or a noun if you were in the same situation as the person is at?
Sure. The first thing, as everyone has, as a majority of them have pointed out, is to evacuate the bus. Make sure that the children are in at a safe distance from the bus. Stop the charging. Make sure that the power to the charging infrastructure is cut off. And of course, have all, because the fire suppression method or means is nearby, use the right means to put out and use the fire extinguisher to put out the fire, even if it's just a smoke. As long as you can cool the cells in the battery pack, you can prevent it from becoming a bigger hazard, catastrophic hazard.
Brilliant. Thank you so much, ma'am. This brings us to the end of the webinar, and I thank all my lovely audience that they have still stuck in with us till 8:20. It is quite late in India hours, IST. However, they were quite nice and polite that they were still, with us all throughout. So I would like to thank you, especially that you were so busy, but still you took out so much time, to explain everything in such an easy manner. I know these are like quite complicated topics, and one slide could be one lecture in one semester. So hats off to you. Thank you, team of UL, namely Rindu, and all the audience. Our funders, without whom this webinar series would not have been possible. A quick note to the audience, other than thank you and Eid Mubarak, is that the presentation and the link for the video in YouTube would be uploaded in a week or so. So you'll be getting a notification in your mails. And if not, do keep checking in the link where you have registered for. So there will be the video for the same, the PPT, and also all the questions that you have sent me, which unfortunately due to time constraints, I could not take it. We will give it to the speaker, and as public query, we will upload all these 3 documents in the same link. Lastly, if you have any comments regarding this webinar or any new topics that you would want us to cover, please do not hesitate to mail me in shravani.sharma.wri@wri.org, or alternatively, you can also reach out to me via LinkedIn, and that is just simply Shravani Sharma. So that brings us to the end of the webinar for today. See you next month. And before that, ma'am, would you like to give any last words as closing? Yeah.
Yes, I would like to thank everyone for attending. I know it's a day of festival as well as, pretty late at night for you. So I appreciate you joining this webinar. And as Shravani mentioned, you can always send the questions and we will do our best to answer all your questions. And I would like to thank WRI for giving me this opportunity, and hopefully we can do a few more with WRI, and Shravani especially for organizing this and doing a great job. Thank you.
Thank you so much, ma'am. Thank you, audience. See you next month with a new and exciting topic. Have a lovely evening. Eid Mubarak. Bye.
Bye-bye.